Hi, welcome to this video on intermolecular forces. So in this unit, we're going to be talking about the forces that hold one molecule to another molecule. So it's a little different than bonding. So when we talk about bonding, we're talking about intramolecular. That's the difference. So intramolecular means within the molecule. So this is going to be bonding, like ionic or covalent, whereas intermolecular is really important because inter is the ones that hold one molecule to another, or they are between molecules. So we can see over here on the right that here is molecule 1, molecule 2, and then this right here is the IMF. Well, it holds one to the other. So they happen because there's an unequal distribution of the electrons in the molecule. And so there's an electrostatic attraction. So electrostatic meaning positive is attracted to negative of one atom or one molecule to another. This affects the changes of state. So this is really what we're going to focus on, is the properties that it affects, which is the changes of state. So your solid, liquid, or gas. So melting points, boiling points, all of those things are affected by causing changes among the molecules. So it keeps the molecules the same. So remember that it's a physical change because the molecules are staying exactly the same. So these are physical changes. All right, so physical properties such as melting points, boiling points, vapor pressures are all going to be attributed to the strength of the intermolecular attraction. So it should make sense. The lower the boiling point, meaning the easier it is to boil or melt, is going to be a weaker IMF. So that just means that it takes less energy, right? So less energy to overcome the IMF. So that should make sense because they're weaker. And then the higher the boiling point, the stronger the IMF is going to be. So here you can kind of see solid, liquid, gas. So when we look at different states of matter, we've got a gas versus a liquid versus a solid. Obviously, when we're comparing one substance, if something's existing in the solid phase, that's probably going to be a stronger IMF than something that's in the gaseous phase. That's usually going to be a weaker IMF. We can make this connection, decision as long as we're looking at the substance at the same temperature, because temperature does affect the state of the matter. So if I'm comparing two different substances, let's say carbon dioxide, or in this case, for example, down right below, is gasoline. So if I have gasoline versus water, gasoline evaporates much more quickly. So we know the intermolecular attractive forces that hold gasoline molecules to each other are weaker. So it's more likely that the gasoline would be in the gaseous form because it vaporizes very easily, and then your water is in the liquid form. So that usually tells you that the water, we know, is if they're at the same temperature, would have stronger IMFs. In fact, the water molecules are held together by a strong IMF. It's the strongest. It's called hydrogen bonds. We're going to learn more about these in just a few minutes. So the types of intermolecular forces, we're going to spend a little time on this. Okay, so we're going to do these types of intermolecular forces. These are going to be strongest to weakest. So that way you can kind of put them in reference. So we're going to start with our strongest, which is dipole-dipole interactions. So dipole-dipole is exactly what it sounds. We talked previously about polarity. So when we have polar molecules, a polar molecule is a molecule that has a pole, because it has uneven electrons sharing. So therefore, on one side of the molecule, there is a partially negative sign, and on the other, there's a partial positive, because one side has more negative electrons. And so what happens is these two polar molecules, will have a force of attraction or attract to one another. That's what a dipole-dipole is. So you can kind of see down here in this example below, we've got hydrochloric molecules. So I've got HCl. So when we look at what's going on in terms of the attraction, we know that the chlorine is more electronegative. So therefore, the chlorine gets a partial negative side and the hydrogen gets a partial positive. And so if I have two of those HCl molecules next to each other, then of course they're going to attract to each other. So we're going to have this IMF right here. That's called dipole-dipole because it's the dipole attracted to the dipole of another molecule. So polar molecules are going to have that uneven charge distribution, and their dipole moments are not canceling. So that's the key of why we have to understand that they're polar. And we spent some time on that. Compounds that exhibit this type of IMF are going to have higher melting and boiling points than those that exhibit the weaker IMFs. So if something has dipole-dipole, we tend to think it's going to have higher melting points, boiling points. At the same temperature, it's more likely to be a liquid or a solid. Doesn't mean it can't be a gas, though. So hydrochloric acid molecules in this example down here are held together to each other by the dipole-dipole IMFs. And the chlorine's pulling the electrons in the bond with a greater force than the hydrogen, so the molecule becomes polar, right? And then the two neighboring molecules are aligning so that the charges are oppositely aligned, and then they can attract to each other. All right, so moving on to our next IMF. The next IMF we're going to talk about is hydrogen bonding. So hydrogen bonding is actually a special case of dipole-dipole. So that's why you don't see another number in front of it. So it does fall under dipole-dipole, but it is a special case of dipole-dipole, and it is the strongest IMF we have. So this one's going to be the strongest. So the forces of attraction in this case are specific, and so it's still a dipole-dipole. So it's a hydrogen atom on one molecule that's attracted to the unshared electron pairs on fluorine, oxygen, or nitrogen atoms. So for example, with water molecules, so I'm going to draw just a water molecule. I've got those two lone pairs, right? And so when I have another hydrogen or water molecule, right, we see that there ends up being an attraction between the lone pair and the hydrogen. So this is the IMF, or the hydrogen bond. So really important, okay, is they're not real bonds. So we don't want to confuse hydrogen bonding with a bonded hydrogen. So a hydrogen bond is not a real bond. It's just the strongest of the IMFs, so they call it a hydrogen bond. But it's not an actual real bond. A real bond would be right here in between. So that's a covalent bond. So that's not the same thing. So be very careful with that. So the strands of DNA, so some other examples of things, the strands of DNA that make up our genetic code use hydrogen bonds. So remember, there's the nitrogen on the strand of DNA. That nitrogen's attracted to the hydrogens on the other molecule, and that's what holds them together. But keep in mind, we can break those strands of DNA and unzip them so that they can replicate and things, but they go right back together. So it doesn't change the DNA. So that's important. We're not breaking bonds when we change the hydrogen bonds. The unique physical properties of water are due to the fact that it has hydrogen bonding. So it has really high boiling points and high specific heats. That's because there's a strong attraction. So you can also see in this picture, again, reminding you the hydrogen bond is between the molecules, right? And the actual bond, or covalent bonded hydrogen, because that's what it is in the molecule. So there's a difference there. You have to make sure you understand those differences and you don't confuse them. Because if you refer to it the wrong way on the test, it's wrong. All right, so moving on to the boiling points and stuff. So there is a large variation in boiling points among covalent hydrides, so of the group 14 through 17. So for example, let's say like carbon hydrogens versus nitrogen hydrogen, right? Like this kind of scenario. Oxygen to hydrogen, hydrogen to fluorine, or fluorine to hydrogen, I guess I should say it that way so I can keep it consistent. So there's a large variation in boiling point when I go this direction, right? And the reason has to do with hydrogen bonding. There's an especially large variation when I go from CH to NH. We see a very large jump in boiling point. So the reason is these lighter hydrides, especially the ones like water, HF, NH3, the ones that are not group. Let's get rid of that. Those lighter hydrides, the period ones, elements, or period 2 elements, I guess is what they really are. The period 2 elements that are with hydrogen, those are going to have really high electronegativity values, which then make them very polar. So they're especially polar. So that the more polar something is, the stronger the dipole strength is, and so then it's going to have a stronger IMF. So more polarity has a stronger dipole. So when we compare, fluorine to hydrogen has the strongest dipole, so then that's going to have the highest boiling point, usually. Okay? Now, the other issue, though, we have is that when atoms are lighter or smaller, right, the distance between their dipoles is a lot less. So then we also have that issue. So what ends up happening here is we see a little bit of like in between these two things. Really, F to H does not have the highest boiling point. O to H does. That's because this one's so small. Okay. The lighter atoms, so the smaller the atom, or the radiuses are, there's a smaller distance between the dipoles, right? So therefore, it strengthens the attractions, and then the attractive forces are going to dissipate with increased distance. So they're more strongly held the smaller they are, and so we're going to actually end up having a little bit smaller dipoles. All right, so the hydrogen bonding, and we'll talk about some different examples of this as we go through it, and I'll explain it a little better. The second type of IMF you want to be aware of is the ion dipole. The ion dipole is exactly what it sounds like. It's when you have a charged ion, right, and you bring it near a nonpolar molecule. So if you look over here on the left, you'll see that you've got a nonpolar molecule right here. So it's a nonpolar means it's not charged. All the electrons are evenly distributed. But what ends up happening is, and I'm going to shift this over just a little so I can see it better. What ends up happening is that you bring a charged molecule, a charged ion towards it, and when it gets close, it actually attracts the electrons, and so then it creates an uneven distribution, and so then the electrons, it disrupts the electron cloud. So basically the ion pulls the electrons in the electron cloud closer, and then it polarizes it and transfers it into a temporary dipole, which allows the ion's attraction. So it'll make this partially negative, and then this side becomes partially positive because some of those electrons will shift over to be closer to that ion. So you can induce a dipole with a charged ion. We can also induce a dipole with another dipole. So the force of attraction between a polar molecule and a nonpolar molecule. So in this case, this is the right-hand side picture that you see. So in this picture, what you're seeing is that we've got a nonpolar molecule, and then we've got this, we bring a polar molecule next to it. It's the same idea with a dipole-induced dipole, is it's the same concept as the ion. So the polar molecule has the partially negative charge, and so then that's going to shift, right? Or actually, I drew that the wrong way. It's going to shift the electrons away from that negative side. So then this side becomes partially negative, leaving a partially positive side. So the force of attraction between the polar molecule and a nonpolar. So the polar molecule induces a temporary dipole in the nonpolar molecule, so it causes it to be slightly polarized. Larger molecules are more polarizable than smaller molecules because they have more electrons. So typically, if it's the more electrons it has, the more likely it is to shift electrons over towards, or in this case, away from that negative dipole. And larger molecules are more likely to form these induced dipoles. All right, so it can happen, but it's more likely to happen in larger molecules than smaller molecules. So like CH, this wouldn't happen very good with a CH molecule, like a methane. All right, so our next, and one of also very important, commonly seen IMFs is London dispersion forces. So London dispersion forces are a force of attraction between two nonpolar molecules. So it's basically due to the fact that they can form temporary dipoles. These are, again, make sure you realize these are very temporary. They do not last for long periods of time. Nonpolar, they'll basically constantly like form, break, form, break, form, break. So they're very temporary. They're weaker, okay, much weaker. So typically, nonpolar molecules would have no attraction to each other at all. So they're not going to like each other. So it would be more similar to what you see in this little gray picture, is two nonpolar atoms are just going to hang around and they normally would not care. Without the forces, though, we wouldn't have any liquid gases or solid liquids or anything like that. So basically, anything that was nonpolar would never be able to form a liquid or a solid. I think I said that wrong a second ago. They would never form those attractions. So then they would never form liquids and solids, which is not true because we know like dry ice exists, right? Which is nonpolar CO2 molecules that are attracted to each other to make a solid. So what happens is with London dispersion forces is they are a function of the number of electrons in the molecule and how tightly the electrons are held. That's the key. So it's all about how many electrons it has. So the more electrons it has, right, what's really happening is there's collisions. So when collisions occur between the molecules, okay, the electron cloud is going to become distorted because as they basically collide into each other, they create a collision. So if you look down here at this bottom, at this picture right below, you can see that they're using atom A and B, which would be like molecule A and B of hydrogens, right? So we're assuming H2, which is easy because it's nonpolar. So initially, atom A and B, we would imagine that all the electrons would be evenly distributed like you see in this picture, right? So there's no polarization at all. However, when they do collide, it creates an instantaneous dipole. And so really what ends up happening is there's uneven electron distribution. So when they collide, you'll notice, it's hard to tell kind of on this picture, but this side that's closest to the atom becomes partially positive, and you'll notice there's less electrons in that area. So there's less electrons in this area over here. So you know it's hard to see, but that's kind of showing that the electrons have shifted over more towards the other side. So that's what it means when it says polarizable. So it's a momentary induced dipole. The amount of distortion of electron cloud is referred to polarizability. The more distortion there is, the more polarizable it is. So since the molecule has a positive and negative side, it can be attracted to other molecules. So we end up creating basically this partial negative, partial, positive side. And then it'll actually induce dipoles in the other atoms around it as well. So then these two, right, will be attracted to each other through that induced dipole. So it's really, there's just an instantaneous dipole. It'll appear and then disappear very quickly, but it keeps them attracted to each other. So the molecule now has that positive side and the negative side, right? So that's why it's attracted. But polarizability is an important word to know. So when the more distortion you have of the electron cloud, meaning when the electrons get shifted more to one side, it's considered more polarizable. So usually there's a way to figure out how polarizable it is. So all electrons are going to have, so all molecules have electrons no matter what, and all molecules are going to have dispersion forces. That's a key. All molecules have dispersion forces. Even stuff that exists like with hydrogen bonding as its main intermolecular force, like water, still has dispersion forces as well. And these forces can range from 5 to 40 kilojoules per mole, meaning some of them are stronger than others. The strength is this key right here. So this is really important. Make sure you know the force increases as the number of electrons increases due to increasing polarizability. So if you increase the number of electrons in the electron cloud, it will become more polarizable, meaning it's more likely for those electrons to shift to one side. And so then that's going to be an increased strength of that dipole-dipole. So more electrons tend to have more polarizability and tend to be stronger. To better understand an induced dipole IMF, we can look at the halogens. So halogens are easy because we can see all of them very easily as all in the same column. So they're all nonpolar. So you've got F2, right? Oh, I was going to actually draw the structure and then I didn't. So we would have an F single bonded to an F. They're all single bonded, right? And then we're going to have the chlorine. So again, same thing. When we look at all these, they're all nonpolar. We got bromine. So one of the things you're going to notice, you should notice, is on the periodic table is that we see fluorine and chlorine as gases, bromine is a liquid, and then iodine is a solid. So now we want to consider, well, crap, hold on, let's think about this. Like why, if they're all bonded and their Lewis dot structures all look exactly the same, they're all nonpolar, why would iodine and bromine exist as a liquid? Well, we have to go back to that concept of melting boiling points and things like that. And that means that when we see that iodine is a solid, we know it's going to be a stronger IMF. So what we're trying to explain is, how is it stronger? Because they're all nonpolar, which means the only thing they can have is London dispersion forces. They can't have anything if they're nonpolar other than London dispersion forces. So it has to do with the polarizability or the number of electrons that their molecule has. So bromine, for example, let's talk bromine, is larger than fluorine or chlorine. So it has more electrons and is more polarizable. Electrons are in constant motion, so it's reasonable that they could occasionally pile up on one side of the molecule. So, for example, when we see these two atoms together, right, we might see that the electrons get piled up more on this side, right, of the molecule. And so when they get piled up on this side, right, and then we have a few over here, but not as many, this becomes partially negative and this becomes partially positive. And then when we have another bromine molecule around, it's going to attract that pretty strongly because it's going to have a pretty strong negative charge on that side. So that temporary positive and temporary negative poles are really strong. So this is kind of like it sets off like a chain reaction, and it induces a whole bunch of its neighboring molecules to also have those, and then they all attract to each other. So then we can have the same thing happen in iodine. But iodine is even larger, So it has even more electrons and is even more polarizable. So the more number of electrons it has, the more polarizable it is. Basically, the stronger the negative side would become and the positive side would become, because there's a lot more electron density on one side of the molecule. And so the attractive forces become greater when that happens. So the IMF between molecules of iodine, so let's be careful on that. So it's an iodine. Oops, I'm going to erase that really fast. So when we're thinking about this and we're talking about it, we're talking about this iodine molecule and another iodine molecule. So we're talking about one sample of pure iodine. Now keep in mind, we can also have these attractions happening in mixtures. But right now we're only going to talk substances that are not mixtures. But basically this becomes partially negative, partially positive, because we have the distortion of the polarizability, more electrons on one side. And so then this side of this molecule would be partially negative, this side would be partially positive. It would induce that. Remember, this is the IMF. That's the London Dispersion Force IMF, not within. So it's not talking about that bond on the inside. It's talking about what holds the two together. All right, going on to. All right, so here's kind of a brief overview of the intermolecular forces, so that you can kind of see it in a table format. Hopefully this will help you kind of visualize it a little better. So first thing you want to think about is it's like a flow chart. What are the interacting molecules or ions? So first, are ions involved? So if there's ions, then you're going to say yes, and are the polar molecules and ions both present? If they're both present, then you have ion dipole forces, right? Like KBr in water. If it's a no, this would be usually like a dissolving kind of solubility scenario. We're not there yet in our notes. Or if we say no, then we're going to go to ionic bonding. So that means there's only multiple kinds of ions, right? Which then would have nothing to do with IMFs at all. If ions are not involved, then you have to decide if there are polar molecules involved. If there are polar molecules, right, then you have to decide, is it hydrogen bonding? So are hydrogens bonded to nitrogen, oxygen, or fluorine atoms? And we would say, if we said yes, then it would be hydrogen bonding. If we say no, it's dipole-dipole. So here's some different examples. And then are polar molecules involved? No, then we're going to have London dispersion forces only. So that means the only thing you can have is the induced dipoles based on polarizability. You'll notice down here they call them van der Waals forces. Van der Waals is like the biology term. That's the same thing as London dispersion forces. So that's exactly the same. So remember, we talked about all of these molecules can have London dispersion forces. So keep in mind that's why that's showing that all-encompassing. But the only London dispersion force, only forces that nonpolar molecules can feel is the London dispersion. They can't feel anything else. All right, let's look at this little example problem that we put in here. All right, so exercise 1 says, why do you think that HF has a significantly higher boiling point than HCl? So let's look. So when I look at where HF is, so here's HF, and then it's comparing HF to HCl. So I'm looking for HCl, it's way down here. Okay, so what do we see happening as we go down the group? So remember, this is going down your group. So we have HF to HCl. So first off, we've already talked previously, but are those polar? And so hopefully you're realizing, okay, HF, HCl, they're both polar, right? So since they're both polar, they're going to exhibit dipole-dipole forces, right? So when we look at what's going on with their polarities, we have to think back about dipole-dipole. The stronger the polarity, the greater the polarity is, the stronger the dipole becomes. So fluorine is our most electronegative element. So since fluorine is the most electronegative element, right? And it should kind of be the same with NH3. It's going to have the stronger attractions. So we're comparing it with NH3 as well. So When that's the case, it's this. Oops, H, H, H. Okay, so when we're comparing any of them, either way, fluorine, and I'm not going to be able to fit this in, is the most electronegative. And since it's the most electronegative of the elements, it creates the strongest dipole. The strongest dipole attraction, which is then going to be the strongest dipole-dipole interaction. So therefore, it's going to require the most energy to break apart. So I would add that in there somewhere too, into your notes. So I know you can't hardly even read that anyway, so it's terrible. We'll go over it a little more in class, but write that down somewhere. I'll try to rewrite it. Let me rewrite it a little nicer. Okay, so that way it's a little easier to see. Okay, so fluorine is more electronegative. I'm going to use En. Okay, which then means it has an increased dipole strength, I guess is a better way to say that. An increased dipole strength, which then means it's going to have an increased dipole IMF, or attraction. And then that's going to take more energy to break, to overcome. So since it takes more energy to overcome it, it's going to have the higher boiling points. So it has to do with the strength of that dipole. Other than the first compound in each set, why does the boiling point trend towards upwards? So the first set, we see a decrease, right? But then the rest of them, we see jumping upwards. What happens as we go down a group? Because that's essentially what all those are. We're going down the group. What's happening to the polarizability of the atoms? So let's think about that. So it doesn't matter what it is. What happens to as we see distance or size, right? We know that as we go down the group, we're increasing the number of electrons, right? So therefore, it's more polarizable. So therefore, we have increased attractions. So therefore, it means that the shift of electrons is greater. So there's a greater shift in the electron clouds. Even if they are polar, we still have London dispersion forces. So we're going to see that the London dispersion attractions, or LDF attractions, are going to get stronger. So we still have our polarity, our dipole-dipole, but now we're increasing the strength of those dipoles because of the polarizability. So that's why the boiling points are going up as you go down. So the larger the atoms become, with the exception of that very first drop down, because that's a big drop in that very first from period 2 to period 3. That's a big drop in distance. So we see a huge decline in boiling points. And so what we notice is that we almost switch over. So the polarity of the molecule is not as effective as what the London dispersion force attractions are. All right, then the next question says, why is group 4A, the bottom curve, consistently the lowest in each period? So group 4A is the same as 14. So the bottom one, why is it consistently the lowest? And so it's asking us to consider this one right here. But that's because almost all of those are nonpolar. So C to H is a nonpolar bond. right? So it only has LDFs. Whereas the others, so it only has LDFs, and all the others are going to have, those are all going to have hydrogen bonding here. And then as you shift, right, we end up with dipole-dipole. So everything else has stronger IMFs, either hydrogen bonding or dipole-dipole. These all right here are going to be only London dispersion forces because they're tetrahedral. And so when they're tetrahedral like that, they're always going to be nonpolar bonds, nonpolar molecules. So there's no other option. So they don't have any other stronger IMFs. So they're existing only based on their London dispersion forces. So that's why we see in that whole group all the way down, they're always going to be slightly lower than the other elements in the other groups that are on the same period. So, all right, so we have to think about strengths. Remember that we can have more than one IMF affecting two molecules. So they can, that's what we're seeing in this example here. But you need to make sure you understand the strength of each IMF, how to identify them. We'll work on that a little more in class. How to identify the different IMFs, and then how to distinguish or relate those to boiling points and melting points in solid, liquid, gas states. Because we're going to be adding on and talking about solid, liquid, gases a little bit more in detail coming up.